Hello everyone, my name is Joshua Donkles and I have renamed my project to Object Classification in the Movable Feast Machine. So originally my goal was to or create a convolutional neural network for that could be used in the Movable Feast Machine. And my first goal was, hey, MNIST, it's a simple example, 32 by 32 images, I could easily implement this. And I was completely wrong, just because of the scale of how much stuff would go into that and the complexity of the communication networks and everything like that. Because, for example, this is an example of what a MNIST convolutional neural network would look like. A couple convolution layers, hyperbolic tangent layers to kind of normalize the results, average pooling, which means it just scales it down by averaging the results by half, so it'll scale it down to half the size. And you think, oh, this doesn't seem that bad, but it's very complicated in the movable feast machine, um, and just the scale of it. Because if you think about it, 6 convolution layers, 16 convolution layers, 120 convolution layers, and then 120 fully connected layers, to actually have that visible and just working together, I think it'd be very difficult. Um, so I scaled it down a lot. So I'm using a similar example. This is what I based it off of, but through a lot of testing and a lot of trial and error, I have scaled it down to a 3 by 3 image, which requires one convolution layer and one fully connected layer. Now originally I thought I would need a 5 by 5, 7 by 7, 9 by 9, and I've tested all of those. I built my own custom images for object classification. Now what I mean by object classification is just an image with ones and zeros. So right now this can classify a length 2 line or a dot. Um, in the future I want to scale it up, so where maybe I could do a 5 by 5 image and I can do more objects, or I can add another object in the 3 by 3. I'll just have to figure out a way to train it more efficiently. So 3 by 3, and it takes 12 convolution layers, which isn't bad. And I was able to classify all of them. I got an 80% classification rate through training, and the three images I have tested, I got 100% classification rate. So it's pretty simple. I built my own training images and my own testing images. And then what I got resulted was this, which is the weights that are supposed to be for each convolution layer. I also got weights for the fully connected layer, but that's in a different file. So these weights, though, they're decimal, if you think about it. The movable feast machine doesn't really have a capability of storing decimals, because if you store a double, it's 64 bits, and that's just ridiculous. That's most of an element. So the problem is, how do I store this? So here, let me go into my example. So first let me introduce my elements. So I have these initialization layers. So these are the middle pieces to each layer. So if I start this up, what's going to happen is it's going to spread down, create each layer in the middle, and these will each spread out 4 neurons on each side, which will create the actual convolution layers. So if I play it, so what's happening is each layer propagated down and created themselves. So it's pretty simple. You have these layers, and you have these weights, you have these biases. So these are the weights I'm talking about. You have this huge number, and so how I'm representing it is because conceptually I was thinking about it. When you have decimals and you multiply them, they get smaller. When you have big numbers and you multiply them, they get bigger. So what I'm doing is my basis is a 7-digit length number. So 1865382 represents negative 0.1865382. So let's look at another one of these. 6 length. So this would represent negative 0.0175176. Even a smaller one, negative 2341, would represent negative 0.00023441. So I'm lucky though, in the convolution layers I don't need to worry about that, because all these input images are just zeros and ones. So when I'm multiplying it, it actually doesn't matter. So this will kind of be simple. So I can put any of these images in the front while it's running or while it's paused, doesn't matter, it will pull from it. So let's put image 3 there. Oops, sorry. Okay, so what's going on here, let me pause it, is it's pulling in the neurons, or not the neurons, the pixel values. So every single one here is going to have a pixel value, 1 or 0. So the layer 1 will pull all the pixel values and then propagate it down all the way through the convolution layers. And then once this is happening, when it turns green, it means it's multiplied it. So your weight is negative 2,341, and you multiply it by the pixel. This gives you your new pixel weight. So then if you look at this one, what you're going to get is this weight and this pixel, but that value is not the same. Because what's happening is the weights propagate. Let me finish this out. The weights propagate in because you're applying a dot product. So the nice thing about having a 3x3 image and a filter the size of 3x3, which is this, you just have to multiply each one by a pixel and then apply the dot product to the matrix. And once you have the dot product, then all you got to do is add this bias to it. Now what the bias does in a convolutional neural network is it just allows for more flexibility in what things can be classified, because it just adds that one more variable that can change when it's being trained to allow for classification. So once these are added, I can't store it here because sadly I ran out of space. I have the weight and the bias, and they can get pretty big. So in the 4th neuron of each layer, I store the actual output result. So this new pixel weight is going to be the actual resulting pixel weight from this layer, which isn't that bad. I mean, and it stores, and it will be easily propagated down into this fully connected layer. So that is not implemented yet, but they have weights, they have values, they have biases, but I just don't have it propagating down, going through the fully connected layer and outputting a result. I don't believe that will be that much more work. I should be able to get it done within the next week for the demo, and that's about it. Trying to think of what else. So also in here you have your layers, so it just kind of tells you what layer you're on, your position in the layer, and yeah, that's about it. Oh, I also made it a little robust. So for example, you can't actually see it happening too much, but so what's happening here is these middle pixels, these initialization neurons, are constantly recreating these. And so if these get erased, the values get reset. So it'll re-go through grabbing the pixels, grabbing the values, grabbing everything. If I erase this and I run it, so it's re-grabbing the values. And then if you look at this value hasn't changed. Because why would this update? It still has its value, but it doesn't need to actually get its value from anywhere else. And if you look at these have still updated too, because the weight's 5.7, but the new pixel weight's this. So it still propagates through, it still does everything required. So I'm hoping to continue making this robust, and hopefully you can be able to erase half the thing and it will still propagate, recreate itself, and then wait for that until it finally classifies the image or the object. And that is my project.